Hello.
Hello.
Mhm.
Nice to meet you. Can you hear me?
Yes, I can.
I'm very sorry for the delay. So could
Okay.
you share your slide for testing?
Yeah, 1 second. Let's see here. Can you enable screen sharing, please?
공유 기능이 아직 안 돼 있다는데요. Just give me a second.
Cool.
You try again.
Okay. 1 second. Okay. Let me move this over here. Okay, cool. So, try it again. How does that look? Does that work?
It works. Okay. So could you
Oh, perfect.
go back and forth just for testing?
Yeah, good call. Yeah. So that works, eh?
Yeah,
Cool.
it works. Yeah,
Great.
great.
Perfect.
Yeah. And thanks
Awesome.
for the accepting the invitation, and also congratulations on your recent papers in science.
Oh, thank you. Yeah, I'm excited to be here. Yeah, this is great. I appreciate the invitation very much. So,
Yeah. So we will start the webinar within a minute, so you can just take a rest for a minute.
okay, I'll go get a sweater. Yeah, I'll be right back.
이가 되면 시작하도록 하겠습니다. So this is the international webinar on the carbon neutrality. We are going to start the webinar at 11 o'clock. Okay, good morning, everyone. This is Jeong-Gi from the School of Energy and Chemical Engineering at UNIST. So you are now participating in the international webinar on carbon neutrality, which is supported by UNIST Carbon Neutrality Institute and the UNIST Office of Public Relations. Today we have the special speaker, Dr. Gregg Beckham, who is from the NREL, National Renewable Resource Energy Lab, actually. And personally, it is my great honor and pleasure to have him as our distinguished speaker. So let me briefly introduce his academic background. So he got his PhD, bachelor's degree in chemical engineering at the Oklahoma State University in 2002. And he then moved to Boston to get his master's and PhD degree at MIT in chemical engineering. And he got NSF graduate fellowship and MIT presidential fellowship. And then he got a position at NREL in 2008, and he was promoted to senior research fellow and group leader at NREL in 2018. And he is also affiliated with the Department of Chemistry at University of Colorado Boulder and Department of Chemistry at the Colorado State University. And he got a lot of prestigious award. so including some the Young Investigator Award from the many societies like the ACS, AICH, RSC, and SIMB, Society for Industrial Microbiology and Biotechnology. And he is recently started to leading the BOTU consortium, which is supported by the US DOE. And he is also actively organizing some conferences, including Golden Conference for lignin biorefinery, and he's also going to organize the conference on the plastic recycling and upcycling in 2023. And he got a lot of the editorial advisory board membership, including Kansas Chem Cell Report, Physical Science, and blah, blah, blah. So anyway, so far he published more than 200 papers, and he is a world-renowned leading scientist in the field of biorefinery and the plastic recycling. So let's welcome Dr. Gregg Beckham with big hand. And now, Gregg Beckham, Dr. Beckham, you can share your screen. Okay.
Let's see here. It worked a second ago. There we go. Okay. Okay. Does that look good? Can you see my slides?
Yeah.
Okay.
Yes.
Perfect. Should I go ahead and start then?
Yeah.
Great. Well, I sincerely appreciate the invitation to be here with you all virtually, at least today, and really appreciate the kind introduction as well. In putting my talk together, I thought I would tell you 3 stories, some of which are partly published and some of which are unpublished, but all really focused on the idea of chemical recycling of today's polymers. And before I jump into the talk on chemical recycling of plastics, I first wanted to just very briefly mention NREL and the mission of NREL. For those of you who are not perhaps as familiar with our lab, or maybe not at all. And so NREL is a US Department of Energy national laboratory, one of 17 in the United States. We work only on energy efficiency and renewable energy applications. And so that involves things like how do we produce energy using solar, wind, geothermal, marine power. How do we use energy both in homes and offices and buildings, as well as how do we use energy to move ourselves around. And then all of this is sort of rolled up into this concept of systems integration. And so how does the penetration of renewable energy onto the electricity grid affect things from an economic and a life cycle and an economy-wide perspective? How do we incorporate batteries or thermal storage or other types of energy storage systems? And then NREL works with, of course, federal agencies, state and local government, and many international collaborators. But we also work very closely with private industry. We're one of the smallest US Department of Energy national labs, but we have more industrial collaborations than all of the other labs put together, which is really just speaks to, I think, the importance of sustainability and carbon neutrality. Of course, you all know that. It's all why we're here. But also speaks to the translational research, sort of approach that NREL takes. And this is the laboratory. So here is essentially, if you can see, hopefully you can see my mouse. But the laboratory is set here on the south side of this mesa, which is a beautiful place to go running and biking. And then Golden is over here in sort of on the other side of this mesa. And then in the background, you can see the snow-capped Rocky Mountains in the back. And for those of you who don't know, this is Golden, Colorado, and this is where the home of Coors Light is. So the Coors biorefinery is actually just on the other side of this mountain over here, on the north side of this mesa that we're on the south side of. And so certainly if anybody is over this way and would like to visit us at NREL, please, of course, reach out to me and let me know anytime. We would be very happy to host you, and we have many international visitors, both just for a few days, but also people who visit for weeks to months to even up to a year on sabbaticals and things like this. And so if that's of interest to anybody, please, of course, feel free to reach out to me. And so I wanted to talk today and focus today primarily, as noted on the title slide, about plastics chemical recycling approaches and new developments that we and our collaborators are attempting to make in this space. I think all of you, of course, know this very well. This is in the popular press all around the world, almost seems like on a weekly basis these days, and has been for the last 5 or 6 years at least. And that is really the challenge associated with plastics pollution. It's really everywhere. Of course, many dire images of plastics in the ocean. Many of us have seen those dire images of aquatic life caught in fishing nets, and the sort of bottles in the guts of whales and things like this. But I think it's also, really plastics waste is really found essentially everywhere researchers are looking. This is from a paper from Jessica Bronny and colleagues that was published 2 years ago in Science. She was a PhD student at the time. She was looking across the mountain west in the United States. We have many national parks here, including some that you may have heard of, like Rocky Mountain National Park, Yellowstone, Canyonlands, Grand Canyon, of course, etc. And she was looking at particulate matter carried by prevailing winds from the Pacific Northwest down through the Mountain West. And she kept seeing these colored pieces of things on her under microscope images, and realized very quickly that they were plastics, and that there was literally plastic rain being put down in protected areas of the United States. And this is one of many studies like this. And of course, plastic waste is associated with disease on coral reefs. We all know these kinds of things as well. But really, the point is that it's pollution from plastics is basically found everywhere researchers look. But I think it's, while many of us, of course, know that plastics waste is a pollution problem from a solids perspective, it's also a climate and an energy challenge. And I think this is really important for those of us who are working in this space or want to work in this space, to make this point to the broader community. There's a lot of talk these days about sustainable aviation fuel. Certainly, that's a massive need. We and many others are working on that, of course, around the world. But the pre-pandemic global aviation sector uses basically the equivalent amount of fossil fuel consumption to the polymer manufacturing sector as well. And so this is on the order of, in terms of global carbon use, on the order of aviation. And this is only going to rise with projected population growth in the electrification of light-duty vehicles. It's projected that 1/5 of our global fossil carbon consumption will be plastics, or for plastics manufacturing by 2050, unless we change the way that we do this. And of course, where we have good data here at NREL, based upon US supply chains, we alone use around 3 quads of energy. And a quad is quite a large unit of, this is about 3% of the energy use of the United States alone every year, just for plastics consumption, which is really crazy. And you can see, a lot of these plastics, of course, are things like the polyolefins. PET is a big one, PVC, and polystyrene, as well as other categories of plastics. And recycling today, again, I think many of you know this, of course, but recycling, especially in the global north and the developed world, is really mostly limited at scale today to mechanical recycling. And mechanical recycling is basically a very fancy separations approach, right, on very dirty substrates and very mixed and heterogeneous and contaminated substrates. The 2 primary plastics that are recycled, at least in the U.S., where I'm familiar with, but I think mostly globally, are PET bottles, single-use beverage bottles, as well as high-density polyethylene, HDPE. And the challenge really there with mechanical recycling, although I think it's a great technology for those 2 plastics, is it's really downcycling for PET bottles. Those PET bottles tend to go into fibers for clothing because of deleterious reactions during thermomechanical recycling and extrusion, where chain breakages are introduced, and that reduces the polymer property quality during recycling. And so, but beyond PET bottles and HDPE, of course, there are many other plastics. And there's overall, at least, where I'm familiar with most, there's very little economic incentive for reclamation. And so there's not a lot of deployment beyond HDPE and single-use beverage bottles. And even then, there's usually very little economic incentive for their recovery. And mechanical recycling, of course, is not ubiquitously applicable or universally applicable. it can't work on multi-layer packaging. It doesn't work on textiles. It doesn't work on construction waste. Doesn't work on tires, and the list goes on and on and on. And so a couple of years ago, we founded this consortium called the Bottle Consortium. BOTTLE is an acronym. It stands for Bio-Optimized Technologies to Keep Thermoplastics Out of Landfills and the Environment. And so we work in this consortium on sort of what's shown here in this placemat slide. We work on plastic waste that can be recycled, but it perhaps is not at sufficient scale. But we work on a lot of materials like textiles, consumer goods, and things like this that are not recycled at all today, including packaging. And what we do, and what our ultimate goal is to deliver scalable and selective recycling technologies that enable cost-effective recycling, upcycling, and energy efficiency improvements for plastics manufacturing, use, and recycling. And our mission is twofold, and I'm going to tell you about the first today primarily, and that is to develop basically processes to recycle and upcycle today's plastics, and also to develop new plastics that are inherently recyclable by design. We're guided by techno-economic analysis and life cycle assessment very closely, and we use analysis tools like TEA and LCA to choose between options of thermal, electro, bio, and photocatalysis, depending on the feedstock. We deconstruct those into small molecules like you would in any kind of chemical recycling approach. And then we take these small molecules, whether they be a single molecule, a few molecules, or a very, very large mixture of molecules, as I'll tell you about at the last part of the talk today, and we convert those into upcycled materials that are higher value to create an economic incentive for recycling, as well as we work on bio-based and waste-based plastics that are infinitely recyclable. BOTTLE is a consortium of 10 member institutions, 5 Department of Energy labs, Argonne, Los Alamos, NREL, Oak Ridge, and SLAC, and 5 universities, Colorado State, MIT, Montana State, Northwestern, and the University of Portsmouth in the UK. And so what I'm going to tell you today is 3 stories. And I hope that these are of interest. Some of these are partially published, and some of them, actually one of them just came out last week. So what I'll tell you about in this order, I'm going to briefly talk about work that I'm really excited about. Usually I really love talking about these enzymes that work on PET. This has really captured the imagination of many folks in the community, and there's a lot of folks working on enzymatic hydrolysis of PET. I'll talk about glycolysis of PET as well, and so this is sorry, let me go back. Sort of an interfacial catalysis approach, and then a homogeneous catalysis approach to break down PET, in both cases. And lastly, I'll talk for about half the talk on homogeneous catalysis of mixed plastics and the conversion of mixed plastics into single products using a 2-step catalytic and biological process. And this is really focused on polymer science throughout most of this, and I will note, besides the polymer science and the reaction engineering and the chemical catalysis, the biocatalysis, there's a lot of problems that we can't tackle alone. I don't expect a single institution, a single group, a single consortium to be able to to address these problems realistically at scale. And so I just wanted to note that collaborations are extremely welcome across any and all of these things. And certainly this is a global problem, and it's going to take global teams to solve these challenges. And so the first thing I'll tell you about is PET, polyethylene terephthalate, enzymatic hydrolysis. And this was really where we and many other people in the community got excited. It was known since about 2005 that cutinase enzymes were reported in 2005 and engineered through the mid 2000s and the early 2010s to be able to depolymerize PET into terephthalic acid and ethylene glycol. But I think it was really this paper, and this is a beautiful example of microbiology done extremely well from Yoshida, Oda, and coworkers. And what they did was they sent sort of a small army of PhD students out to dig in the dirt outside of a Japanese PET bottle recycling plant. And they were looking for a single organism that could degrade PET. And I apologize, there's the ChemDraw translation error here. But anyway, they found this one organism with bacterium, Edionella sacchiensis. And what you can see here, there's a filament of PET, and this biofilm of bacteria is Edionella sacchiensis growing on that filament of PET. And this organism secretes this enzyme PETase, as well as which PETase works on the polymeric PET. It liberates bis hydroxyethylterephthalate, or BHIT, monohydroxyethyl terephthalate, or MHET. And then another enzyme, metase, comes along and cleaves monohydroxyethyl terephthalate, or hydrolyzes this into terephthalic acid and ethylene glycol. And we and many other groups saw the structure of this. There was many prominent papers coming out on this in 2017 and 2018, solving the structure and beginning to engineer this this enzyme. And since then, many papers have come out in this space. But one of the things that I think is really important, the Edianellapedase, the leaf compost cutinase, which was discovered by a group in Europe, engineered by a group in the US, and then further engineered by a group in France, and published in a paper in Nature in 2020. It's the best enzyme there is out there today, more or less. But this is really a major challenge with all enzymes, including that leaf compost cutinase enzyme and the Edianellapedase, and that is PET comes in varying forms of crystallinity. And so PET in single-use beverage bottles tends to be on the order of 30% crystallinity. In textiles and carpets, it's on the order of 40% crystallinity, roughly. And in thermoforms and food packaging, it tends to be on the order of less than 10%. And what's shown here, this is enzymatic hydrolysis experiments in a pH-controlled bioreactor. These are all done at the 1.5 liter scale with that leaf compost cutinase enzyme that was engineered by Carbios and published in Nature in 2020. And what you can see is if you look at the low crystallinity PET, you're able to essentially get nearly to quantitative conversion. It's about 95% plus conversion. But when you use essentially bottle grade PET or highly crystalline PET, around 32% in this case, you can see that the enzymatic hydrolysis tops out at about 20% conversion. In crystallinity of PET substrates, this is a major hurdle for realistic enzymatic PET recycling, because the energy intensity needed to take this kind of polymer over to this type of polymer is quite substantial. And I'll show you why on this slide. This is how Carbios and others are proposing to take in both textile grade PET as well as bottle grade PET and turn this into amorphous PET that enzymes are able to work on. So, and we modeled this and we published this. This is based upon the process concept from Carbios, published in Nature in 2020, as I mentioned. And this model was published by Avantika Singh in our group and co-workers in Jewel in 2021, so last year. And we modeled basically the Carbios process where they take in clean flake, they do a thermomechanical extrusion of this flake, and then they cryo grind it after extrusion. And this feedstock pretreatment enables the reduction of crystallinity from around 30 to 40% down below 10%. However, and I should say, and then the rest of the process is essentially the enzymatic hydrolysis step, and then this goes through a downstream processing step to recover ethylene glycol, a sodium sulfate salt, and then recycled terephthalic acid. So your two primary building blocks, EG and TPA, of your PET. The challenge with this, though, is that 50% of the energy consumption in this process is in this red box. And so this pretreatment consumes 50% of the energy and emits 50% of the greenhouse gas emissions to this process, making it such that virgin PET manufacturing is actually more energy efficient and more GHG advantaged than enzymatic PET recycling through this process. And so we were interested, and this is in collaboration with John McGeehan at the University of Portsmouth and other colleagues, in understanding, can we find enzymes from natural diversity that not only were thermophilic and can operate around 65 to 70 degrees C, so right around the glass transition temperature of PET, where enzymes have found to be most efficient, but also can we find enzymes that are active on crystalline or semi-crystalline PET substrates? And so this is work from Erica Erickson and Jafet Gado. This is in revision now, and I hope that it will be accepted very soon. And so what we did was thinking about, how can we screen all non-redundant protein databases like JGI, NCBI, and others, and use not only bioinformatics like hidden Markov models, but also use machine learning. And this is work from Jafet Gado on the machine learning piece to predict not only will a sequence, from sequence alone, will we have both a thermophilic enzyme, but will we also have an enzyme that is able to work on PET at thermophilic conditions. And so what we were able to isolate was 74 enzymes, or I should say identify and predict that they would have PET degrading activity with 74 enzymes. And what you can see is if you look at clades, these are different clades. So clade 1 through clade 7 around this circle. Clades 7, 6, and 5 had enzymes that were previously reported. All of the enzymes like Edenella, leaf complex cutinase, T. fusca are all over here in clade 6 and 7. But once you get out here into clade 4, clade 3, clade 2, and clade 1, none of these have ever been reported before. And you can see from this phylogenetic tree that the diversity, once you get out to clade 4, is quite substantially different than clade 7, which is all very closely related, and clade 6, which is still very, very close phylogenetically. And so we purified we synthesized the genes and the plasmids for expression of all 74 of these enzymes. We went through purification trials with all 74, and we were able to get 51 enzymes that were able to be expressed, purified, and assayed for PET hydrolysis. And what we did was we assayed these as a function of temperature from 30 to 70 degrees C and pH from 5 to 8. And we looked for activity on two different substrates, an amorphous powder and an amorphous film, as well as a crystalline powder, so actually 3 substrates. And what I'm showing you here are selectivity differences in the enzymes from amorphous powder to crystalline powder. And what you can see, this is just for a small subset, but this is basically the take-home message for all of this. We found only a single enzyme that has actually preferential activity for a crystalline powder, and this was really exciting. And this is the enzyme in particular, and we were interested in why it has better activity on crystalline powder. I don't have the answer for you, but one hint that we do have from the structures, which we solved, this was before AlphaFold 2 came out. We solved this with Google DeepMind. We sent them all 74 structures on a Friday, and they sent us all structures back on a Monday morning. This enzyme has a higher surface charge, the one that's able to act on crystalline PET. We don't know if that's the reason why this is better, but we're currently working with Harvard University, the University of Portsmouth, and not shown here, the University of Manchester, to do directed evolution on this crystalline active enzyme to be able to attempt to understand the reasons why it is active on crystalline substrates. And so that's quite cool, and this is a nice discovery, we think. And but we still don't have a good model for how these things interact with PET substrates, including both crystalline and amorphous substrates. And so that's where that study is now, and we hope that that'll be published soon, as well as then we'll follow that up with directed evolution of that particular enzyme that is quite active on crystalline substrates, with the idea and attempt to be able to hopefully evolve enzymes where you can avoid that pretreatment of the PET and going from, say, 30 or 40% crystallinity down to less than 10%. And by doing so, that would be a massive savings from an energy and a greenhouse gas emissions perspective in this process. And so what I wanted to do next is I want to switch gears and talk about PET glycolysis. And what I'm going to show you today is this process that we have been working on in collaboration with IBM, as well as with Northwestern University, with Linda Broadbelt's group, as well as with Chris Tassoni's group at SLAC in Stanford at their Linear Accelerator Laboratory. And so this is now, instead of an enzyme, we're using a chemical catalyst, in this case, an organocatalyst. This is a very simple catalyst. This is triethylamine. Many of you know this is a common laboratory reagent. It doesn't smell very good, but it's quite a basic molecule, as you can see, and probably know. And it has quite a low boiling point, much lower than the reaction temperature of 190 to 220 degrees C. And in the presence of ethylene glycol, one can do PET glycolysis to make bis hydroxyethyl terephthalate, which conveniently can precipitate from ethylene glycol as a solvent. And here is the process flow diagram that we're pursuing. So we take recovered PET, we put that into a depolymerization reactor. We filter out residual solids that are left over after the reaction, do decolorization and metals removal over ion exchange and activated carbon columns. And then we crystallize BHET from that, which we can filter off and dry and then repolymerize into PET. Ethylene glycol is recovered and recycled to the depolymerization reactor. And fortunately, this is a volatile catalyst, and so catalyst recovery is quite straightforward. If you release the pressure of the reactor at reaction temperature, the catalyst is volatile and can then be distilled and recycled very easily. And so this is work that's led by Bob Allen at NREL, I should mention, as well as Nicholas Rohrer. And we're working on writing a paper on this now. And so here's our reactor and our experimental setup. This is extremely simple. All of the reactions for the kinetics that I'm going to show you, the kinetics data I'm going to show you, were simply collected in these Swage-Lock union type reactors. And this is quite simple. Basically, you take ethylene glycol, triethylamine, PET, and this essentially at reaction temperature becomes a single phase. And then after after a reaction, you have monomers and oligomers left if you go to high conversion extents, which then you can essentially filter out hot to be able to recover your excess ethylene glycol, and then recover monomers, dimers, and trimers when you filter this hot. And so I'm going to show you a lot of gel permeation chromatogram traces. And I just wanted you to note that in all of those, the monomer has been separated from the residual polymer after reaction. So just so you're aware in these GPC traces that I'm going to show you on this slide. And so this is essentially the molecular weight distributions from partial conversion reactions, going from 0 minutes all the way up to 90 minutes. And you can see 90 minutes is the one here in this dark brown. And you can see, of course, as you would expect, a reduction in molecular weight in the uncatalyzed case, but it's not very dramatic in the uncatalyzed case. Whereas when you have the catalyst around, triethylamine, of course, you get essentially only small molecules that are present and very little residual oligomers. And so what this tells us and suggests to us is that uncatalyzed glycolysis is dominated by random chain scission, and the catalyzed glycolysis chemistry is much more complex. And so we're quite interested in building a kinetic model and a mechanistic model of this chemistry as well. And so this is work that we're doing with Linda Broadbelt's group. She's a world leader in kinetics modeling for polymer synthesis as well as polymer deconstruction. And so taking the data on the left-hand side of the slide, which are these gel permeation chromatogram or molecular weight traces of PET, we're able to then plot this as in terms of molecular weight MW as a function of time. And what you can see is a really dramatic drop-off in the MW right at the initial part of the reaction. Polydispersity, PDI remains constant. And this is over, just a few, extents of conversion, up to about 20% extent of conversion. The MW has dropped from 12 down to about 6 or so. And so you get this really early and dramatic decrease in molecular weight. And if you look at this in a different way, so now plotting MW as a function of conversion, so measured by total aromatic monomer yield, as a function of temperature, all of these collapse onto a single curve essentially. And if you do the same thing with molecular weight, log 10 of molecular weight as a function of log 10 of conversion as well, sort of starting up here at low conversion and going to high conversion, again, you get a collapse onto, from a polymer physics perspective, you get a collapse of MW onto a single line. And so what this really looks like, if you know polymer synthesis, this looks like step growth kinetics, except of course going in the opposite direction in this case. And we also see concomitant polymer crystallinity changes during the reaction, going again from this powder substrate and now showing ex situ DSC traces. The remaining solid, as you would expect, becomes more crystalline before you get to high extensive conversion, when you start to see reduced crystallinity at the higher extensive conversion. And we've been working, as I mentioned earlier, with Chris Tassoni at SLAC at Stanford to be able to then do both in situ and ex situ small angle X-ray scattering, as well as wide angle X-ray scattering, such that we can collect larger features in the polymer physics behavior, as well as smaller features with small and wide angle X-ray scattering, respectively. And so this is what we've come up with so far as a mechanistic sort of cartoon-like model for PET catalyzed glycolysis from these scattering data. And so in regions 1 and 2, this is essentially at the start of the reaction, you have these crystalline regions and these amorphous regions shown in red and blue respectively. You have some initial cold crystallization, and this is followed by deconstruction in the amorphous region, and that's what's shown where the crystalline regions are still intact. But this leads to a really rapid drop-off in molecular weight and an increase in crystallinity. And then during region 3, the chains become starting to be degraded now in the crystalline regions, and so you're getting cleavages in the crystalline regions. And then at region 4, this is basically now at high conversion extents. Instead of random chain scissions, this is when we think we're starting to see chain incisions, as the PET deconstruction occurs in both the amorphous and crystalline fractions at an equal rate. And so that's a molecular picture and sort of a macromolecular picture of this process. What about this process at scale? And so, like I showed you for the enzymatic PET hydrolysis, we've also built a process model in Aspen and built a techno-economic analysis and life cycle assessment of PET glycolysis. Again, this is what I showed you earlier, now drawn out in a little more detail. You have a catalyst and ethylene glycol, you clean PET flake, you run the reaction. This goes through a flash, and so you can recover your catalyst and some of the ethylene glycol. This goes through a filter to remove solids, activated carbon to remove junk, dyes and pigments and all kinds of other things. It goes through ion exchange to remove any metals, and then it goes through a BHET crystallization step, a centrifuge. You have BHET, which you can then repolymerize into PET, and then you can make recycled PET chips. And then separately, the liquid from the centrifuge will go through a distillation column. You'll remove excess water, and then the ethylene glycol at the bottom of this column can be recovered and recycled to the reactor. And so here are the economics and the environmental impacts for this glycolysis process, or the predicted one at least. So this is recycled PET from this PET glycolysis process, the minimum selling price. And you can see immediately that more than half of the minimum selling price is the feedstock. And so if you can access feedstocks beyond clean PET flake, this is a very conservative analysis with a substrate that we can buy today at scale, which is clean PET flake. But if you can imagine reducing this dramatically, like for carpet or waste textiles, where this will be almost zero, you can see that the overall minimum selling price will be reduced dramatically. And what's shown here, this is virgin PET historical prices at different intrinsic viscosities. So useful for fibers, useful for bottles. And this is in green, again, in a conservative case where we think the rPET from glycolysis could sit. And you can see more or less it's always below virgin PET prices. And again, thinking about reducing the feedstock dramatically, you could even reduce this more. From a life cycle assessment perspective, now looking at virgin PET again in orange and this rPET from this volatile catalyst process or glycolysis process shown in blue, you can see that we still have some work to do, right? And so if you look at fossil fuel depletion, it is a reduction. So you want, in this case, blue to be smaller than orange. It is, but not by much. And we still have work to do to reduce the energy intensity. The same thing with global warming potential. Yes, it is reduced over virgin PET production, but not by that much. And so there's definitely some work to be done here still. Water use is, again, close to the same. And so process improvements certainly still need to be made. Okay, so then with the last part of my talk, this is a bit, I think I have about 15 slides or so on this process. This is another example story from Bottle. And this was just published last Thursday. And we're very excited about this paper. And so the idea here was, how do we take mixed plastics and make a single molecule? And I'm going to tell you how we did that using this two-step catalysis and biological process. And so I probably don't need to tell any of you in terms of the chemistry of plastics that are out there today. The chemistry of plastics is extremely complex, but there are three primary linkages that connect monomers together in most plastics. That's carbon-carbon bonds, carbon-oxygen bonds, and carbon-nitrogen bonds. And if you look at the carbon-carbon containing backbones of polymers, that's what's shown in the orange here on the left-hand side of this image. This is from a paper in Nature Catalysis, a review in Nature Catalysis that we wrote last year. And this is global annual consumption in millions of metric tons per year. Most of the plastics that we consume, with a few exceptions like PET and polyurethane and nylon, are carbon-carbon backbone containing molecules like polyethylenes, polypropylene and PVC, polystyrene, and then rubbers, etc. But mixed plastics are going to have all of these carbon-oxygen, carbon-nitrogen, and carbon-carbon bonds in them. And this is really a challenge. And so we were thinking about, how do we go beyond pyrolysis? Pyrolysis is very well known. There are a lot of challenges with pyrolysis still at scale, but some companies are trying it out at scale, at least especially for polyolefin-rich waste, although again, there's a lot of challenges there. And we wanted to do something different. And so can we go beyond pyrolysis, which is basically going to convert some plastics back into plastics, but also some plastics into fuels, and therefore releasing a lot of the carbon into the atmosphere. And so we came across this idea from a paper published in Catalysis Today in 1995 from Walter Partenheimer. And he was a global leader in the AMCO mid-century process. and studying and developing this process at scale. And this today is how paraxylene is converted into terephthalic acid through this auto-oxidation catalysis process at the 80 million metric tons per year scale. And the way that this works is you have some hydrocarbon substrate in the case of paraxylene or xylene or toluene, and there are multiple steps that occur. This process uses bromine for a radical initiator, and so bromine removes an electron and initiates this reaction, thereby activating oxygen with this radical. And cobalt and manganese are essentially metal promoters that are able to promote beta fission reactions and oxidation, further auto-oxidation reactions through this process. And towards the end of his career, Walter Partenheimer started trying this mid-century Amico process on a lot of different substrates. He tried this with cellulose, with cotton, with lignin, as well as with single plastics. And there's this beautiful patent that he wrote and was published in the early 2000s. And what he showed, and we got really excited about this, is you could take the mid-century Amico process, which uses cobalt, manganese, bromine, sometimes with a little bit of zirconium, in the presence of water, in acetic acid mostly though, at fairly mild temperatures and fairly short residence times. And you could take, for example, polystyrene and make, you can see 73% yield of benzoic acid. This is a great idea. Let's go try this for mixed plastics. Who's a world leader in oxidation catalysis at University of Wisconsin-Madison. But this is shown now or illustrated for HDPE. And so you have, again, some initiator. It removes a hydrogen atom, you form an electron, which activates oxygen, and then you get these alkoxy radical species that cobalt and manganese can then promote beta fission reactions, and so you can cleave carbon-carbon bonds. And so the idea was, can we cleave carbon-carbon bonds in like things like polyethylene and polystyrene, as well as CO bonds in PET. And I'm going to show you very quickly that yes, we can do that. And so in all of these cases, I'm going to show you we purchased commercial standards, as well as we went to the grocery store across the street and we bought styrofoam cups. This is for polystyrene. This is in acetic acid, 8-bar oxygen, 5.5 hours, and we can obtain around 66% yield of benzoic acid. We do the same thing for polyethylene, in this case HDPE. We bought beads from Sigma Aldrich. We went across the street and bought milk containers, which are HDPE here. In this case, we can run a bit lower in temperature and a bit shorter in residence time, and we can make about 35% yield or 34% yield of C4 to C22 dicarboxylic acids. And for PET, again, and these are all the optimal conditions I'm showing you now at 210, for 5.5 hours, we're able to obtain around 68% or 66% of terephthalic acid as a single product from PET depolymerization through this auto-oxidation process. When you mix these together, shown on the top is for polystyrene and HDPE. This is 5.5 hours, 180C, running at the temperature and residence time needed for the most recalcitrant plastic. You see the polystyrene benzoate yields are fairly similar. The yields for dicarboxylic acids go down by about 10%. And that's because deleterious reactions can consume these and oxidize these to CO2 at these longer residence times and higher temperatures. When you combine all three plastics, now running at the conditions for PET, optimal, I should say, for PET, again, 5.5 hours, you can see, again, a slightly lower yield of DCAs from polyethylene, but similar yields for benzoic acid and terephthalic acid in this mixed plastics case. So that's quite cool. But then we make this mixture of products. And so how do we deal with that? And so we had this idea about 10 years ago for lignin, and we thought, well, we can apply the same idea of biological funneling to mixed plastics. And so what is biological funneling? So the idea is, can you take all of these mixed oxygenates that are bioavailable, they're close to water soluble in their salt forms, and feed them to an organism that you engineer all of the metabolic network in this host to produce a single compound. And we thought that would be quite fun in this case too. And so that's exactly what we did. So we took an organism, Pseudomonas putida, KT2440. We have a lot of experience with this organism in our group for lignin and sugar conversions from a biorefining perspective. And it natively will consume acetate, which is a residual solvent. It will natively consume benzoate, which is a native carbon source. In previous work, we had engineered it to consume terephthalic acid. And in this work as well, we engineered it to consume dicarboxylic acids. And we made two different products. We have two separate strains. The first one, we thought it would be fun to have basically, let's just produce one molecule only from the aromatic components. And then the second strain, we were like, we thought it would be fun to make a single molecule, PHAs, from all of the substrates. And so I'll show you the data on first, the aromatic substrates converted into a single product. And so now again, acetate and the DCAs go to growth, and the benzoate and terephthalate go to beta-ketoadipate. On a molar yield, starting with the aromatics alone, you can see we're able to reach 75% yield from the beads, essentially all in a mixed case. So that is pretty cool. And this is making a product from all the substrates now. So all of the products go to both growth and polyhydroxyalkanoates. And you can see, as you would expect, when grown on these mixed substrates, the organism is able to produce polyhydroxyalkanoates, which is really, really exciting. And this is, I should say, the natural carbon storage product of this organism. So in the presence of, or I should say the absence rather, of exogenous nitrogen, but an excess of carbon, it will accumulate PHAs natively. And so we're quite excited about this. We think that this hybrid process where you first use an oxidative step, to take especially hydrocarbon-based plastics with no oxygen in them and very little bioavailability, you use the simple, industrially relevant, already massive scale chemical oxidation process, and you can make these oxygenated intermediates, which then can be fed to an organism or a consortia even to make a tunable bioproduct. And so what we're doing now is we're expanding this to other large waste scale polymers like polypropylene, rubber, ABS, polyurethanes, nylons, etc. We're also conducting techno-economic analysis and life cycle assessment to figure out what are the best products to make. And then lastly, working with Eugene Chen, who's a world leader in recyclable by design polymers, we're going to try to make bioproducts that can go into polyolefin replacements, but that are inherently recyclable at the end of life chemically. And we're really excited about that work with Eugene. And I should also mention all of the catalysis and biology work that we did was in close collaboration with our colleagues at MIT and the University of Wisconsin-Madison, particularly Yuri Roman and Shannon Stahl, as well as collaborators at Oak Ridge, namely Adam Gus. And so I'm almost done with my talk. I just wanted to leave you with a few brief thoughts on plastics recycling, upcycling, and redesign, just as kind of some conclusions. And so I think it's extremely critical that we as a community, we have many, many ideas. We all want to solve this problem. This is a global challenge. It's going to require teams of collaborators from academia, from government research, from industry certainly, and I mean industry as startup companies all the way to huge household name companies. We all have many ideas, and we will all work together, hopefully, to solve these problems and across international borders. But I think it is so important that in all of our work to use resources efficiently and to be able to come up with solutions in the near term that will help the planet. We must use analysis early and often to understand if our processes are going to be better than business as usual. And so there's many technologies to make this idea work, but they must be better from an energy cost and GHG perspective relative to current plastics technologies. And we have tools to do this. And these plastics require accurate baselines. We published work on this, at least for US-based supply chains. And I also just wanted to end and say, I think it's also extremely critical that lessons from the biomass conversion community have shown that, especially in catalysis, biocatalysis, and process development, when substrates are poorly characterized, it's really hard to replicate results in other labs. And in doing so, I think it's really important that we as a community source base polymers from Sigma Aldrich, from Goodfellow, and from other places that anyone in the world, no matter where you're at, can buy the same polymer or similar or close as possible to the same polymer and run their chemistry on that as well, or their biology or their process. And I think it's important that we do this very carefully. And then lastly, this was mentioned in the introduction, but I just want to say we have a new Gordon Research Conference in 2023. This is the first instance of this. This is being organized by John McGeehan and me, as well as Kate Beers and Nick Virks. This will be July 9th to the 14th. If you're interested in this topic, I would encourage you to apply to this meeting. Applications are open now. I did, of course, none of the work that I showed you. This was done by a huge team and really wonderful collaborators and colleagues who are shown here. The folks whose work I mostly showed today are Ali Werner and Kevin Sullivan, Kelsey Ramirez, Nick Rohrer, Erica Erickson, Jafet Gato. And we work with a lot of really wonderful colleagues outside of NREL who are shown here, and their names are listed in the order that they're shown here on the right-hand side of the slide. I really appreciate the invitation to be here with all of you today. I'm sorry I couldn't be there in person, but hopefully that was interesting, and I hope we have a few minutes for questions and discussion. So thank you so much. Oh, I can't hear anybody. Yeah.
Can you hear me?
Ah, now I can. Yeah, okay, I can hear you now.
Yeah. So okay, so you can check the Q&A window. So there are some questions. So I have a quick question about utilization of other polyolefin plastics. Is it possible to use polypropylene as well?
Yeah, that's a great question. We've done a lot of depolymerization experiments with polypropylene so far. It works very well. It completely depolymerizes polypropylene. The challenge with polypropylene, though, is the analytical chemistry needed to characterize the products very with high mass closure is extremely challenging because of the branching. We do make a lot of acetic acid. We make a lot of formic acid, but we don't know what else we make, and we see a lot of branched compounds as you would expect from polypropylene. And so we're currently undergoing a lot of work now to basically do LCMS and GCMS to close the mass balances with polypropylene. And we'll plan to submit that paper hopefully in the next couple of weeks.
Okay, so actually I also had a question. So you at the end of the talk you mentioned that you learned some lesson from the biomass utilization studies, right? So in other opposite direction, are there any lesson you can learn from the polymer, plastic recycling or the biomass utilization? Just curious.
Yeah, that's a great question. I hadn't thought about that in that context of going the other direction yet. But I think more generally, there are so many similarities between them, right? Between biomass and waste plastics, they're low value, diffusely distributed, heterogeneous, highly contaminated, oftentimes mixed chemistry polymers that are very low density as well in most cases. And so I think, a lot of the things that, around pelletization, and so to answer your question, there is an infrastructure for collection of some waste plastics today. And if we could apply the same principles of collection to waste biomass, that might be an interesting place. So from a logistics perspective, that might be interesting to think about. I've never thought about that. That's a good question, though. So yeah, I need to think about that a little more.
So there are many other questions. So
Okay.
Pseudomonas is kind of temperature sensitive microbe. Can we try some thermophilic microbe?
Yeah. Yeah, that's a great question. Pseudomonas, I will say, I actually don't think it's that temperature sensitive. It is a mesophile, though. Um, but as long as you have temperature controlled bioreactors, that's usually not that big of a deal, not that big of a problem. And I will say the other thing that Pseudomonas has going for it, besides incredibly fast metabolism and very broad catabolic capabilities, is it has extremely high toxicity tolerance to nasty molecules that, like aromatic compounds that many organisms don't tolerate very well. But that said, we only use Pseudomonas in this study because that's what our group knows how to use. And of all the reasons I said already, we don't use E. coli because Pseudomonas is faster growing. Many times it's more toxicity tolerant, has a much broader catabolic capability. But frankly, you could use any organism. You can use yeast, you can use fungi, you can use any bacterium, including thermophiles, for this approach, as long as you can engineer in the appropriate pathways to consume the building blocks. Pseudomonas is just an example, an exemplary microbe in this case, that we think has some advantages, but it's not the only one that's applicable here.
Okay, thank you. And there's also a question about the potential application of beta-ketoadipate.
Yeah, great question. I'm sorry that I didn't mention that when I was going through the slides very quickly at the end. So beta ketoadipate, of course, is a C6 dicarboxylic acid. It has a beta ketone, and it looks like adipic acid, basically with that beta ketone group added. And so we've put it into nylon 6,6 analogs. We put it into polybutylene adipate terephthalate analogs. And the cool part about the beta ketone is it makes the molecule much more rigid than adipic acid. And in doing so, it increases the glass transition temperature, or reduces water uptake. And so you can make performance advantage nylons that are much more easily recyclable, as well as polyesters that have the same properties as PET, but instead of having an aromatic block, they have an aliphatic block. So they're much more easily biodegradable.
Okay, there's one more question. In the metal removal chamber, which type of reaction you performed? So like you remove the metal via salt formation or something like that?
I suspect, or I assume that question is about the glycolysis chemistry. And in that process, yeah, I mean, we're using ion exchange. So we're just trying to remove metals via ion exchange. That said, that's a really challenging part of the process because for condensation polymers like PET, only a small amount of iron or other metals that are quite quite ubiquitous in these waste streams can inhibit repolymerization into new high molecular weight polymers. And so I think that the downstream processing and metals removal from things like PET glycolysis, that's quite a challenge, and I don't think that's been solved at scale yet.
Okay, so I think, there are a lot more questions actually. So because time limitation, I think we can have one or two more questions. So for bio-based plastic, C14 analysis guarantee the content of biomass originated carbon. I wonder how to confirm that the rPET comes from waste PET.
Yeah. There is a paper recently published from Mike Shaver from the University of Manchester where they have presented and new methods for how to do that. I am not as familiar with that work as I should be, but that's where I would suggest going to look first. We are attempting to deploy that method currently in our own group from Mike's lab to be able to measure these things as well. Yeah, but it's a great question. I'm sorry I don't have a very good answer for you. So
very active discussion. So one more thing, is there any future in polymer upcycling utilizing AI and machine learning like similar to AI drug discovery? And some software from Merck to use electroanalysis could help.
Yeah, that's a great question. One of the things that I didn't talk about today is the Bottle Consortium's effort in designing recyclable by design polymers. We have a paper that we're about to submit, and we're going to put a computational tool online that allows you to predict the thermal properties, mechanical properties, and barrier properties of thermoplastics from the monomers alone. And so it basically is a machine learning tool that we've spent 5 years developing, and we validated it with about 50 or 60 new polymers that have never been synthesized before in some cases, or at least were not part of the training set for the machine learning validation step. And they predict glass transition temperature and barrier properties very well. And so I definitely think that there's a huge potential for AI and machine learning. And then beyond that, of course, we're using it for catalyst design, chemical catalyst design, as well as enzyme catalyst design for sure. So I think everywhere where you already have a large data set, we should be trying out data science approaches for sure.
Actually there are a lot more questions. Do you have time, or if you have time,
Oh yeah,
we can have one more questions? Okay, I'm sorry that.
yeah. I have.
Uh,
It's 9 p.m. for me, so I have nowhere to go.
okay, so
Yeah.
I think there was questions from the students. So on the first topic, you showed the conversion to monomers. I wonder why it fluctuates a little, very little.
Yeah.
So, and second question is that you investigated weight averaged molecular weight values for molecular weight of the polymers rather than the number averaged ones. So are there any reasons?
Yep. So, so I'll answer the MW versus MN question. Certainly, we measure both. We use both in the models. MW is one that's convenient to show in a talk, and but we definitely measure MN. And all of the experimental data for MW, MN, monomer yield, conversion extent, all of that goes into this kinetic Monte Carlo model that Linda Broadbelt's group has built at Northwestern. So I only showed MW simply for time's sake, and yeah, no other reason. On the, I don't exactly understand the first question in terms of the conversion to monomer, but maybe that's for the oxidation chemistry. Certainly, the temperature differences will impact the monomer yields, especially for polyethylene. In the case of polyethylene oxidation, some of those dicarboxylic acids are not stable at reaction conditions. So the longer you run or the higher the temperature it is, you will get reductions in polyethylene yield, product yields. Yeah.
Okay, so I think uh, we have to wrap up the webinar at this point, and let's thank the Dr. Beckham again. I hope that we have a chance to have an offline some interaction with you in the future, in the near future. Thanks again.
That, thank you so
Have a
much. I
nice,
really
yeah.
appreciate all the questions and discussion. Yeah, thank you so much. And thanks for the invitation. And yeah, thank you so much.
Thank you.
Okay, bye-bye now. Yeah, bye-bye.